Hello everyone, we are Team Zebra and our project is printer real-time torque measurement, which is a continuation from the previous 2 years. Our technical director is Matthew Corvais, who's a mechanical engineering alumnus of URI. He graduated in 2008 with his bachelor's and in 2016 with his master's. Our team is composed of 3 people. Me, Abe Gilbert, who's a computer engineer and will be graduating in 2023. Jacob Rivero, who is the electrical engineer, who is graduating in 2023, and Oscar Schnippering, who is an electrical engineer and will be graduating in 2024. So first, a little bit about Zebra Technologies. It is a multinational corporation that established in 1969 and is headquartered in Lincolnshire, Illinois. It is a market leader in mobile printing technology, and as of May 2022, Zebra Technologies has a market cap of $17.8 billion. It is located in Lincoln, RI for our project, and that location specializes in hardware and software development for mobile printing. The motivation of our project is to continue improving the fixture design, interface the transducer, interface all peripherals to one device, and have that device be on a PCB. We also need to create a graphical user interface that will be able to handle operations of the device and gather and output the torque data as a graph to the user. The best outcome of the project is to interface the transducer, gather the signal data from the device, and then send that data to the GUI to be graphed. It should be have a user-friendly interface that will allow ease of test and fast troubleshooting. And it also should be applicable to all different types of printers. For team accomplishments so far, we have worked on STM32 and consolidated it, linking the IOC configuration and C++ files. We've added a voltage divider that lowers the voltage to the needed level of the STM board so that it does not fry. We also added a low-pass filter, which will obtain more clear data from the torque transducer. And data is now obtained from the torque transducer, sent over serial and saved in CSV format or comma-separated values format. The economic impact of this would be improved quality of printing, which will provide a better product and increase customer satisfaction. It also reduce costs associated with malfunctioning devices, as it will be easier to troubleshoot. There will also be less returned products, as this is costly, and it will be minimized. This is a block diagram of our fixture. Shows exactly how it works with the printer starting the process and sending the step signal data to the STM board. For contributions that I have done, I have worked on mostly the STM32 coding, where I fixed the previous year's code, which had a problem with the files that allowed it not to run. I have also fixed the IOC configuration file, which is needed to add more modules and pins to the microcontroller, which is shown on the right. And both are now synced and work properly together. I also implemented DMA, or direct memory access. So ADC data is now obtained using DMA. Data is then also sent over serial to PuTTY and saved in CSV format. For future accomplishments that I'll work on is to continue working on the external trigger for ADC, as currently the data is obtained during printer pulse, while it should be captured only during the calculated step pulse, which is for the motor pin. The GUI also needs to be fully implemented. It needs to send data to the STM32 code, and I also need to create an easier way to get the saved data in the CSV format to the GUI. To do that, I would create a button that would be in the GUI that would allow the user to open up the specified CSV file in their computer, be able to be graphed. Now I'd like to hand it over to designer Jacob Ribeiro.
Thank you, Abe. Looking at the block diagram, we can see that the transducer needs to have a voltage divider since the signal coming from the transducer is a 10-volt signal. The SCM board would prefer a lower voltage signal for its analog to digital conversions, so I was tasked with creating a voltage divider. The voltage divider's main job is to divide the transducer's voltage across two resistors in series to the output. The resulting resistors convert the 10-volt signal from the transducer to a 3.3-volt signal that the SCM board is happy with. I was also assigned to help with the SCM code in order to help troubleshoot issues and find ways to communicate the hardware side of the transducer and the SCM board to the software side to get the data that we need out. I created a proto board with both the voltage divider and a low-pass filter that Oscar designed to ensure stable connections for the hardware to get and read out. Understanding the data that is coming out of the transducer is important in order to know what types of values we need to expect. The transducer gives us a voltage range that is used to calculate the torque measurement that we are looking for. With a voltage value and range that we get from the transducer, we will calculate the torque inside Python code in order to have the process done off the STM board. My future contributions for the ABO are continuing to help Abe in order to change the step signal pin from the printer step signal to the motor step signal. The next phase would be to help get the particle brake working with the apparatus and understand how the code will work with the new testing equipment. I will now hand it off to my partner, Oscar.
Thank you, Jacob. And now we're going to have our third and final look at the block diagram. And one can see the low-pass filter, my main contribution, and exactly where and what it does within the system. So the low-pass filter lies between the voltage divider and the STM board. And the purpose of the low-pass filter is to take a noisy signal, which is coming from the transducer, and to attenuate unwanted frequencies and noise. And once the noisy signal has been filtered, it will go to the STM board where it can be processed with greater stability. So the process I took to get the low-pass filter to where it is now started with just the conceptualization of the idea. So our TD, Matt Kurvizi, advised me that last year the teams ran into problems with stalling during the printing and data acquisition process due to frequency spikes and noise. Just within the data stream, there was unwanted high frequencies and noise, and those sometimes caused the stalling of the printer or errors during the data acquisition. Now, Matt advised me that the unwanted frequencies were about 1.1 kilohertz and higher, and just using the simple equation for low-pass filter 1 over 2 pi RC, I was able to come to the conclusion that I would need a 4.7 nanofarad capacitor and a 33 kilo ohm resistor to build a low-pass filter which filters out signals over 1.1 kilohertz. Going off of that, we wanted to include op amps into the low-pass filter, which we originally selected a LM741 op amp, but we were unable to use this one because it relied on a dual rail power supply, meaning we would have had to supply plus and minus voltage, which would have been cumbersome to do within our project. So very early on within the design process, we chose to go with an OPA 340, which is an op amp that only needs a single supply, and we are able to supply the op amps with voltage off of the STM board. So using Multisim, I designed a low-pass filter, and I integrated the active and passive components together. And using the help of our consulting technical director, Mike, he helped me out with simulating the noise and the frequency spikes that we are expecting within the project. And as you can see in the picture, it's the simulation to the construction. So once we simulated the low-pass filter and we were satisfied and confirmed functionality, I went ahead and constructed it on a breadboard. And once it was hooked up to the breadboard, we can see on the next slide that once it was on the breadboard and a noisy signal with frequency spikes was injected into it using a signal generator. The spectrum analysis shows that the unwanted frequencies have been attenuated and the signal is no longer as noisy. So on the top is the input with multiple harmonics up into the megahertz with very noisy and frequency spikes, and on the bottom you can see the clean filtered signal. And the purpose of this is that, once again, the printing process and data acquisition process can move forward unimpeded by any sort of noise or any errors, and that would make our overall project more reliable in its intended application of a testing apparatus. And in terms of my future accomplishments for this project and its anticipated best outcome, we plan on using a particle break in a future fixture, so a whole nother testing apparatus. But at this time, we would like to implement a particle break, which would simulate the torque resistance that we currently use the printer for. So the printer is what's supplying the data that we are measuring in our current setup, but the current setup is limited, or there's sources of error such as temperature, type of paper, the humidity, which all are random sources of error which make our data less reliable. And therefore, we would like to build another one which uses a particle break instead of the printer. And we would be able to program this particle break with more accuracy and be able to simulate the printer without the sources of errors such as temperature, humidity, and type of paper. And so on to what's next for the project. We would like to integrate a graphic user interface with the STM board. So pretty much our goal for this project is that it will one day be used by a theoretical Zebra technician to test printers for the torque of the printer during the printing phases for different types of paper, different types of media, and be able to program and develop the printers using this data. And a graphic user interface would make this easier and more user-friendly for the person using it now. And currently our project, as seen in the block diagram, consists of different phases, different pieces put together. But we would like to consolidate it into a printed circuit board, which would make this project vastly more compact and perhaps even significantly simpler to reproduce and distribute throughout the Zebra company. And additionally, the particle break, as previously mentioned, we would like to create an alternate testing setup which does not rely on a printer and doesn't print anything at all, rather than much rather we use a simulated torque resistance to simulate the printer for more reliable and accurate measurements. Now, the potential risks that are still involved in this project is the relatively long path the data takes from the transducer to the final STM board and the software. Now, there's a couple of different things within there that may cause issues for the data, both in integrity and reliability. So that's something we're constantly working to make sure that the data that we are receiving after going through the voltage divider and the filter, making sure that it's still accurate, but that's a risk. And finally, the data coming from the transducer needs to eventually, using some sort of conversion, needs to eventually be turned into a torque reading in Newton meters or ounce inches. And this is done using a Python script, and potential errors may come from there in terms of the conversion from the data from the transducer into an actual tangible torque measurement. And I'd like to wrap it up by thanking our technical director, Matthew Corvisi. He's been a great help. We're very thankful for his time and his effort towards the project. It's in conjunction with his colleague, Patrick Hagarty. We have been able to make great strides on this project, and we are always within minutes of a answer to any questions, and they're motivated to work on the project with us, and we're very grateful for their time as well. We'd also like to thank our professor, Dr. Harish Sunak, and finally, a very special thank you to Mike Smith for his extensive help throughout the project, and especially for the low-pass filter design. Thank you.